hear me?
Yes, can you
Okay.
turn on your camera?
Yeah. Okay. Just,
Thank you.
okay.
So you can
I
now
can
start.
okay, I can share it first. Okay, can you see this? Okay.
Yes.
Hello again. My name is Ahmad Aboutorabi, and I'm here to present our work auxiliary trajectory planning for real-time vehicle control using MPC model, conducted together with Professor Manfred Gosegelding. And I'd like to thank the organizer for this opportunity, and I I hope that you find this presentation insightful. I will go directly to the problem statement. Actually, consider these two types of the road, the wide and the narrow road. And let's talk about how would the human driver and the self-driving car drive in these two type of the road. Well, it is very important in the narrow road to precisely follow the reference line. So both the human driver and the self-driving car will stick to the defined reference lines. In wide road, the self-driving car, regardless of how wide and narrow the road is, will again define a reference line and stick to the defined reference line. But human driver, when it comes to the wide road, as long as he has the feeling that he is in a safe part of the road, he's less likely to make an abrupt steering to correct every his deviation. I mean, he would drive more relaxed and smoothly and gradually correct his position. In this slide, I will briefly discuss some related work in the area of the trajectory planning. The model predictive controller is well known for its ability to handle the multi-input and multi-output. It's considered the coming information about the reference line and predict the dynamic of the model and use them to generate by optimizing the cost function, generate the best input to the system. Some work or research have been published to increase this adaptability. One of them is the state lattice approach, in which that we use the cost function, another cost function, to select the best trajectory in each situation between all the possible one, and then we define a fixed reference for each situation to navigate. Young and Sakari used the Bezier model, Bezier spline to define more smooth and continuous curvature to improve the computation efficiency. And then actually for a situation, we will have the fixed reference to navigate. There are another method, tube-based MPC, in which that we define the tube around the reference line, and the algorithm will use the different parameters like the weights and prediction horizon to control the vehicle and hold the vehicle in the tube. And another method is the human-like motion planning, in which the algorithm will use the data from the human driving to select the best planning for navigating. In all the method I discussed it, we actually defined a fixed reference to navigate in each scenario, in each situation. Okay, I said that it is safe when it comes to the wide road to have some deviation from the reference line. For example, these two imaginary position of the vehicle in this road is safe. But how much deviation is safe? Uh, for example, for this simple line, simple pass, we can define some limitation the both side, and then based on the width of the auto, we say this green zone, which we call the safe corridor, is safe to be on. I mean, as long as the middle of the vehicle is in this green area, we can say that we are in a safe position of the road. But being in the safe corridor doesn't mean that we are not willing to correct our position or we want to hold this position. The idea is that we say as long as we are uh, on the safe corridor, we are not likely to make abrupt steering. We correct our deviation smoothly and gradually. Actually, this corridor is not constant. It can vary from several centimeters or to meters. In this slide, I showed a safe corridor with initial division. Normally, the cost function of the MPC model should handle two tasks. First, bring the vehicle to the reference line, and simultaneously take care about the coming deviation of the road or curvature of the road. In this work, we want to reduce these two tasks to just one task. In the way, we will say that as long as we are on the safe corridor, we can suppose that we are exactly on the reference line. We do this by defining auxiliary reference, in which, based on our current position and heading of the auto, we defined a new reference, which tends to bring us to the reference line. And it is the important point, it is not a constant reference line. I mean, in each step, we defined a new one based on our current position and the heading of the auto. So as long as we are on the safe corridor, the cost function of the MPC has this feeling that he is always on the reference line and it should only be care about the coming deviation of the road. So to define the auxiliary reference, we use the cubic Bezier curvature or spline, which has four control points. The first point will be defined as our current position. The second one will ensures that the spline is exactly tangent to our current heading of the auto. And the last one will be not defined on the actually the reference line. It would be defined with a offset, because we want to make sure that we are gradually correct our position. So based on our initial deviation from the reference line, we will define a coefficient, which we call that reduction factor, to make sure that we are gradually come to the reference line and we are not rushing to it. So in this slide, I just show the vehicle dynamic. We use the simple bicycle model with a constant speed, and the output is the lateral deviation from the reference line and the heading of the auto, and the input is actually the steering angle. In the cost function of the MPC model, we just use the simple constraint for the input. The important is that the black diagram of the normal MPC is something like this, but in our purpose model, we have the new black auxiliary reference that comes between the reference vehicle plant and the MPC and produce the auxiliary reference in each step based on the situation of the road and the width of the corridor. So to compare the performance of the proposed model with the normal MPC, we proposed three different scenarios. The scenario one is the initial deviation from the straight path. The second one is navigating the curvature without the deviation. And the third one is the navigating the same actually curvature, this time with the noise. So this plot show the result from the actually scenario one, in which we had initial deviation. As you can see, a standard MPC has oscillation around the reference line, but with three different run and simulation with the three different reduction factor, we remove the oscillation. It's our proposed model. And in the blue diagram, as you can see, the red, actually the red plot, which depicts the standard MPC, has abrupt steering, but the other actually method which use the auxiliary reference method depict the actually lower amount of the steering. This is the plot from the scenario 2. As you can see, there isn't any difference between the proposed model and the normal MPC, and the reason for that, which we will going to talk about that is that there was no actually initial deviation or the noise in the scenario. So the both middle show the same behavior. But when it comes to the noisy road, as you can see in the blue diagram, the proposed model in the blue show clear improvement in the steering. So we are not going to, in this scenario, we can see the smoothly corrected position. To show the result quantitative, we define the mean square error for the steering rate. And as you can see, for the first scenario, the value of the MSC of 2.4 thousand, it's by the proposed model, it's now 1.1 thousand, which show that actually more than 50% improvement in the steering rate. The second scenario showed no actually improvement because the reason that we talked about, I mean, there wasn't a noise and the deviation. But the third scenario, navigating the curve with noise, also showed in more than 50% actually improvement in the result of the steering rate. So as a conclusion, I should say that as depicted, actually there was we reduced and eliminated the isolation. And also the MSC value showed that this model can, in a noisy and when there is a deviation, show more improvement in to make the smoother and the gradually correction of the steering and positioning of the auto. And this model worked very good in the noisy environment, which happening always in the real driving. I mean, by the simplified model that we use in our dynamic model and the varying friction in the road and the windy situation and disturbance in the road, we always have the noise, and this model can handle this situation very good. And the concept of the corridor, I mean, the safe corridor aligned very good with actually the driving scenario of the human driving, I mean, the real world. So that was the advantage of this work. And here is some reference that we used in this presentation. And thank you very much for your attention. And I'm here to listen your comments and any question I will answer that.
Thank you for your nice presentation. Is there any question from the audience? If not, I have one. Can you specify what you mean in the title with the auxiliary?
Well, actually, I named this reference as the auxiliary because I just wanted to help the auto actually near the main reference to bring the vehicle. Actually, we will have two reference line. One of them is the main reference, but the auxiliary reference come to action when there are the deviation from the reference lines. And the duty of this auxiliary reference is to bring the vehicle smoothly and gradually to the main reference line.
Okay, thank you. And I think we
you.
go for the next presenter. So we have Sharon Wang from China.
Yeah.
With the
Hello,
top-
bro.
Hello, yeah.
Hear me? You
We can
hear
hear
me?
you. Yes.
Okay. I share my PowerPoint. Let me see. Share.